Okay, so this is the video for our neural networks project. My team consists of myself, Ashik, Joel, and Farouk. Our project is to identify fake Van Gogh paintings. Uh, so we first found a dataset containing around 8,000 paintings by 50 famous artists. And we only focusing on, since we're focusing on Van Gogh, we only took his paintings, which are around 800. And to classify whether they were fake or not, we could not use uh, paintings by other artists as the other class, rather than the paintings not made by Van Gogh, because those artists have their own style and they're not particularly trying to imitate Van Gogh, which is why we had to scrape fake Van Gogh paintings from websites that produce recreations of famous works. So we have around 60 different fake Van Gogh paintings and around 800 originals. So the cells up here are just reading the data and unzipping the files. We have import statements and the CSV file that lists all the artists that are there in the dataset. So here we're reading the file. So this function pre-processes every image. We keep the colors since they are relevant for the image, and we resize them into 256 by 256, which is more manageable. And we read the fake images separately and the original images. As you can see the path here, we run both of those and then we combine them into the original. We combine them into X, and that is what we use as our original data set. And so at this point they are still in the order of originals and then the fakes. I'm sorry, the fakes and the originals. You can see the order here, so I can simply create the labels uh, uh, just by manual one-hot encoding. And once you've done that, once you've created the X and Y, we can do train and test split as we normally do. We use a split of 33%. And once we've done that, we define some metrics here, and this is our first model. So the first classification model that we tried is the VGG16. So for this model, we add a dense layer at the end with two outputs, of course, because we're trying to, it's binary classification, whether it's made by Van Gogh or not, and with, of course, softmax activation. And the model was trained. You can see the different layers, since VGG16 has a lot of layers. And this is a generate actual predicted function which we use to evaluate the function. And here you can see the holdout method that we have described in the report. So we tried this 5 times. So the main problem here is that our data set is very imbalanced, since there are 800 originals and around only 60 different fakes. So when we tried training them on the entire data set, the metrics were very low, or in fact the metrics were skewed because the accuracy would be very high due to the high number of true positives. So to solve this issue, we use the random undersampling technique from the majority class. So what we do is we take 100 random original images and we add the 60 fakes to it, and that is what we use as our data set. So we split them once we've combined them in that way, and then we run 20 epochs, and then we keep track of the scores. So this is similar to holdout, except that the fake images don't change. And we run this 5 times. Every time the original images are sampled randomly, so we get a different 100 every time. So you can see the results over here. So they're in the 70s to 80s range. We have plotted them over here, and you can see the best precision recall is close to 82%. And the title should not be K-fold because it's not technically K-fold, but you can see that around 2 of the different splits or folds, you could say, achieved a pretty high F1 scores. This cell is from before, and okay, so here we have plotted the history from one of the runs. So you can see that the train accuracy increases over time, as well as the validation accuracy, which starts to stagnate after some point. Similarly, the model loss also falls. The train and the validation loss falls gradually. And then here we have the results from the model. So we have the classification report as well as the confusion matrix. So here you can see that from around 22 fake Van Goghs, the model was able to correctly identify 16 of them as fake, while 6 of them were misclassified. Similarly, for 28, for 32 of the originals, it managed to identify that 28 out of the 32 were in fact originals. So it is pretty good. Right. So here we have the ROC curve and the area under the curve. So you can see that it is pretty far off from the line of random probability, which is indicative of good performance. And we come to the second model that we have tried, which is the Inception V3, which again uses the ImageNet weights as was trained on the ImageNet dataset. So for this model, we froze about 20 of the last few layers so that those become, I mean, we left the last 20 layers unfrozen so that they become trainable and the weights change, while the rest of the layers are frozen so that we can retain those weights. And we also added a dense layer at the end for classifying whether they are between the two binary classes. The learning rate is slightly higher here, which was experimentally verified. And Inception V3 has a lot of layers, as you can see here, and we ran 10 epochs on this specific model. We also tried the same holdout method as we saw above, so that the same cell was ran with this create model function, so we didn't have to create a separate cell for it. So from running 10 epochs, the first time we see that the validation accuracy reaches about 81, which is in fact lower than the peak which it achieved. So we can see that the model may have been overfitting, since the train accuracy is increasing, has reached 100% in fact. So you can see here the test accuracy is about 81%, and here you can see the graph. So the train accuracy did reach 100%, while the validation accuracy starts dropping after a point. Similar for the loss. You can see that validation loss starts to stagnate and does not drop after a point. Although we saw different results when we tried the holdout method, which is listed in our report. So again, here you can see the classification report and the confusion matrix. So you can see slightly different numbers. The true positive rate is slightly higher here, but the true negative rate is slightly lower. I think different results. This is from our previous one, I think. Yeah, so those were the two different classification models that we tried. And this is again the ROC curve, which looks quite similar. The steps seen in the ROC curve is due to the few number of samples in our data set. Right. So it says, yeah. So now we move on to the third different architecture that we tried, which is in fact a Siamese network. So for this network, we define these a certain type of triplet that is inputted into the Siamese network, and that input is of the form an anchor image, a positive image, and a negative image. And the Siamese network tries to maximize the distance between the anchor and the positive, while it tries to minimize the distance between the anchor and the negative. So the code you seen here is adapted from the Keras documentation page, where they try to classify between visually similar images. They use a different data set there. It's not for painting forgery detection, but it's for visually similar images. So again, yeah, we pre-process the images here, and we pre-process them into the triplets as I mentioned, and we read them from here. This is not used, as overwritten. It's from a previous run. Negative image paths that we use are in fact Van Gogh paintings. Even this is also overwritten. So these are the negative image paths that we use, which are the fakes, and the anchor and the positive images are read from Van Gogh. So what we do is the anchor and positive are essentially pairs of original Van Gogh. So it tries to create a similarity between Van Gogh, and so it essentially is trying to learn specific painter style. Right, so here we are creating pairs. So we combine them. We create all possible combinations. We take the first 150, of course, and then we create all possible combinations, and then we unpack them into two different lists, because that's how the model inputs them. As for the fake ones, we have around 62 fakes. So we take the first 40, which is about 2/3, and we shuffle them, of course. And yeah, that is used as the negative class. So yeah, this function is here is just to visualize them in pairs. So you can see that the first two columns are the anchor and the positive, while the third column is the negative. So yeah, first two are originals, and while the third is fake. So as for our model, we have for the base CNN, we use the ResNet 50 network, which is a pre-trained model again on ImageNet. And we of course we add a couple of dense layers at the end, which are trainable because the ResNet 50 weights are frozen. So this base network creates an embedding of its inputs, and that's how Siamese networks work, of course. They create embeddings of the inputs that they're given, and then it tries to minimize a particular distance function. So again, this distance layer class is adapted from the Keras documentation page, as well as the Siamese model class. So we have a distance layer that is added to after the embedding layer, and we have a triplet of embeddings. And when the function when the class is instantiated, it calculates the distance between the first two as well as the second two, and returns a tuple of these distances. So that's what the model outputs. You can see the outputs is the pair of distances. So finally, we have the Siamese model, which is instantiated with the Siamese network, as you can see below. This is the particular train step and the test step functions, as well as the loss function that we mentioned earlier. And as you can see that it tries to maximize the distance between anchor and positive, while it tries to minimize the distance between anchor and positive, while it tries to maximize distance between the anchor and the negative. So here you can see the Siamese model training. It took quite some time. We ran 10 epochs, and we can see that the loss drops quite well. From the plot, you can see that the train loss as well as the validation loss drops quite low. It's in the very low regions. So here you can see a visualization of a couple of images, as well as just to see what, I mean, you cannot really relate to the embeddings to them, but just to visualize. So finally, we come to the testing section, which is where we see how our model performs. So here for testing, what we do is we take 22 of the we take 22 anchor images, because we have 22 fake ones remaining. 40 of them were used for training, so that means there are 22 fakes that the model has not seen. And we take similarly 22 anchor images that it has seen, and 22 anchor images, positive images that it has not seen, because the first 150 were used for training. And then we input them into the model. So we create we call model.predict, and we pass a tuple of this form, anchor positive fake, and we do this for every possible combination, which is 22 times 22 to the power of 3, which is 10,648. We could try it with all possible combinations, but I would take a long time, and it would be more representative, but yeah. And finally, this is how we calculate how well the model performed. So the output of the model is of the form, if I can create a new cell here, you can see that result of is of 0 is of this form. It's an NumPy array. It contains two values. So the first value is the distance between the anchor and the positive, and the second is the anchor and the negative. So if you can see that the distance between the anchor and the negative is greater than that of the positive, which is what we were checking here, it means that the model found that the fake one is farther away from an unseen original, which means that it was successful in identifying the fake as a fake one. And you can see that this comes close to about 83% of the triplets that were tried. It can also be visualized through this graph here, where the orange is the negative distance. So in most of the cases, the negative distance is higher than the positive distance. Yeah, so that's about it. More details are